Engineers use light metals because of their favorable mechanical properties. From the fields of aerospace, renewable energy, and electronics, we present some examples of mechanical properties in modern and future applications.
Light metals are important for the aerospace industry, which includes aircraft and also rocket applications, primarily because they're lightweight. But it's not just the fact that they're lightweight. You still need the material to be strong and durable and survive varying amount of heat exposure. So when you combine all these things, aluminum alloys and titanium alloys end up being extremely favorable for the aircraft and rocket industry. Specific strength is an important concept in materials engineering, and all it is the ratio of the strength to the density or the material's weight. And this is important because aluminum alloys, for example, aren't as strong as steel, but they're a lot lower weight. When you scale your design according to that specific strength, that ratio, you can actually find that aluminum is very favorable for many designs.
Aircraft made from light metals consume fuel at a lower rate than those made from heavier materials. Although the structure may be thicker, the overall decrease in weight for a lighter plane is more desirable, making modern air travel affordable and efficient. Today, there are many aluminum alloys to choose from that offer a balanced set of properties to meet a variety of design needs. Advances in aluminum alloy development have created tailored alloys for specific design goals.
So another aluminum alloy that's less common in widespread industry but is an important alloy is the 8000 series, which is aluminum alloyed with lithium. And the main purpose of this alloy is that we still get good strength, but it's even lighter than the other common aluminum alloys. It was used for the Space Shuttle external tank, where every pound or fraction of a pound literally means thousands of dollars in efficiency. So one of the limitations of aluminum alloys is that they lose their strength starting at around 300 Fahrenheit. Another lightweight metal that doesn't lose its strength at temperature is the titanium alloys. Now, titanium is very strong, it's also extremely tough, and it holds up at temperature. Probably one of the most famous examples of the use of titanium is the SR-71 Blackbird. This aircraft travels at speeds that are supersonic. The heat generated on the skins just from the friction traveling through the air requires a material that's going to hold up the heat. Aluminum skins, unlike a commercial aircraft, would never hold up at those speeds. So titanium becomes extremely important to us at those temperatures.
Renewable energy such as wind and solar power is a growing field with great potential for light metals. While small wind turbines for urban use are typically made from aluminum, large wind turbine blades usually use composites. Current research is exploring hybrid fabric metallic constructs to decrease weight and increase efficiency. As this technology evolves, light metals may be key for the improved and affordable harvesting of wind energy.
When considering the design of wind turbine blades, one material that finds applicability is aluminum. It is readily available, it's well understood, it has high fatigue strength, it's lightweight, and we can easily machine it into different shapes that we would like for these blades. One thing that I mentioned there was fatigue strength. That's important because as your wind turbine is cycling, as the wind goes on and off, you are going through a process called cyclic loading. So where you're turning a load on and then turning it off. And what metals are known to do is fatigue. Too much fatigue can cause failure. So we need to consider fatigue when we're designing. So this test behind me, we would do a similar test to this, where we would actually be loading and unloading the specimen. That can give us information about the fatigue strength of the material.
Concentrated solar power is a growing area in renewable energy that uses highly reflective surfaces to collect the sun's rays. Like wind power, this sector sees the benefit of light metals in the development and fabrication of high-performance reflectors.
Another important property to consider is hardness.
Hardness is the tendency of a material to resist localized plastic deformation.
And that's really important when we're considering concentrated solar power. The reason being is that you would want a material that has a lower hardness so that you can easily polish it to a high mirror finish.
When it comes to the production of large reflective surfaces, low resistance to processing results in simpler fabrication and lower production costs. Modern systems like satellites for telecommunications and radars for weather detection use light metals in their manufacture because of their high ductility and low toughness. These properties characterize the formability of the material and can easily be seen in the production of waveguides. Used to transport high-power electromagnetic energy with little loss, waveguides from soft metals can easily be bent into different shapes and at large angles without fracture.
The reason why brass or aluminum is used is because it's ductile, because when you bend this, it's cheap to do quickly. If it was steel, then you'd have to heat it up, and you'd need like a steel smith to make it, but any machinist or any operation technician can make a 90-degree waveguide.
The coefficient of thermal expansion is an important property in the consumer electronics industry. In the design of antennas for cell phones and GPS systems, small changes in length due to temperature can have a significant impact on performance.
Antenna design factors in a lot of the spatial aspects. So one thing that we have is when we design an antenna, what kind of housing and what kind of metal is going to be around it. When we make an antenna, we make it tuned to interact with the surfaces, interact with the sidewalls, things that are all over, everything around the antenna works.
Computer simulations are often used to study how fluctuations in geometry affect signal quality. Differences in temperature result in small dimensional changes which can create poor connectivity.
This antenna here is interacting with its sidewall. So as you can see, the electric field hits the sidewall and this helps the radiation propagate forward. With the thermal coefficient of expansion, if the dielectric tends not to grow as fast as the metal housing around it, this will detune the antenna. As we look further into the antenna, and you can see the fields interacting with the sidewalls. If the sidewalls are not there, then we get a different tuning. So when these sidewalls, if they expanded faster or contracted faster than the dielectric here, we have a little bit of a separation. That separation here at high frequency can cause the antenna to perform worse. You'd have drop calls or you'd have interruption in your services.